Hello, everybody, and welcome to today's webinar from OxTS. Thank you for joining us. You are being taken through today's webinar by myself. I'm Peter Rylands, the Senior Product Manager at OxTS, and walking us through the main body of content is Paris Austin, Head of Product here at OxTS. So a couple of bits of housekeeping first. We are recording this webinar, and it will be available afterwards to run through again in case you miss anything or want to revisit something. Please do ask questions at any time. You can do that in the webinar interface. There will be time for questions at the end, but you can throw them in at any point as you have them, and we'll pick them up at the end. We also have a few polls to run through today, so hopefully you will support us in answering those questions, and that just helps us in our understanding of the market and also helping us to present to you in a way that is more appropriate depending on what your interests are. So hopefully you're looking forward to today's webinar, and I'm going to hand you over to Paris, who's going to take us through how we can achieve centimetre level position accuracy using advanced sensor fusion techniques. So over to you, Paris.
Thank you very much, Pete, and thank you everyone for joining today. So I'm going to take you through hopefully a journey of where we are today and what we do, and what we are striving to do in terms of the strategic work that OxTS are building over the next couple of years. So the main goal of OxTS is make inertial navigation systems and make them as well as we can. And we really pride ourselves on navigation algorithm expertise as well as calibration techniques. So taking individual accelerometers and gyroscopes and calibrating them into an inertial measurement unit that we then use as the heart of our navigation systems. Really, our objectives are to navigate in as many environments as possible, and for automotive customers to date, that has been largely on proving grounds with good view of the sky and RTK GNSS perpetually available. And we know now that that challenge is starting to become slightly more challenging, and that's exactly what the topic of today is about. Assuming that you've got good navigation data though, we have spent a lot of time building application layers on top of the navigation offering. So applications like RT range for vehicle to vehicle and vehicle to infrastructure validation, and also more recently OxTS georeferencer, which is a LiDAR point cloud generation software. Alongside georeferencer, we've also developed a boresight calibration tool so that you can calibrate your INS with respect to a LiDAR sensor. So in terms of our current offering, we have our RT3000 and RT1000 INS systems. They are a combination GNSS and IMU hardware with some intermediate electronics, and we pair that alongside all of that intellectual property that I mentioned earlier, our calibration techniques, our own extended Kalman filter and GNSS processing algorithms, which we refer to as GXIX, which combines RTK processing as well as tight coupling. So we use inertial measurements to feed our generation of our position rather than just supplementing reduction in drift using inertial data. And then assuming that gives us good navigation data output, we feed that data into application software like RT range, so an INS in each car allowing you to do vehicle to vehicle measurements, or single vehicle to infrastructure, or even nowadays an INS to LiDAR, where you are georeferencing data in a global frame and allowing you to make point clouds and maps based on knowing where you were at a given time and where a LiDAR was pointing. So I believe we've got our first poll question now, and Peter's going to ask the question and give you some time to answer.
Yeah, brilliant, thank you, Paris. So just so that this will help us understand who's on the call, it might help us kind of talk about specific elements, or for Paris to talk about specific elements of the content that he's got. Essentially, what is the application that you care about? Please select all that apply, and this will just help us as we work through the content. I'll leave this open for about a minute or so, or until the majority of people have voted. But yeah, interested to know, we obviously work through all of these areas and more. So hopefully you do a few of these things I can see that from the responses at the moment you do. I'll just leave that open for a couple more seconds. And then we can move on. But from what I'm seeing at the moment, we've got generally a majority of people here mainly using an application of ground truthing, collecting reference data. But there's a good mix of survey mapping and autonomous navigation being done here, Paris. So keep that in mind for the content moving forward. Thank you very much, everybody. I'll close this now, and we can carry on with the next bit of content.
Brilliant. Okay, so coming back to the goal of what we are trying to offer at OxTS then is we know that we offer centimetre accurate positioning when on proving ground with open sky, and we do that through the combination of an RTK GNSS receiver and then pairing that with the IMU to give 100 Hz or 250 Hz low latency smooth output for vehicle dynamics, ADAS testing, ground truthing, and also survey and mapping applications. The problem that we face and the challenge is that achieving that 1 centimetre accuracy, even in spite of GNSS outages, is a very difficult thing to recreate because of the nature of the power of GNSS in giving you global 1 centimetre accuracy. In terms of the infrastructure that is there, that a user doesn't have to do anything other than acquire a mobile receiver and configure it correctly and then connect to the existing infrastructure. It's very difficult to recreate that in areas where GNSS is unavailable or you don't have line of sight to satellites or enough of them to achieve RTK. So these alternative solutions are often only relative accuracy, so they're accurate relative to their own coordinate system, which means that if you are comparing your data to globally referenced data, you can have a big problem in terms of bridging that gap between the two data sets, but also purely achieving relative accuracy over time and doing that same accuracy day after day and getting the same reference data if you drive the same route or down the same roads will differ if you have a relative accuracy system. So that's one of the reasons that moving away from GNSS is a very hard thing to replace. So in terms of the options we have in front of us, there's really kind of three that we can see in front of us. The first is to make the most of GNSS when it's there. So take advantage of that infrastructure that has an unbelievable amount of investment in it globally. And now with quad constellation available, there is ever more expanding feature sets that are coming with the GNSS as an infrastructure. But there will always be times when you inevitably do not have line of sight connection to satellites. So the next stage is to maximize the effectiveness of the IMU that we use so that we can fill in those gaps when GNSS is lost. So with quad constellation, the gaps are less regular than they have ever been, but there will still be some, and inevitably if you want to go indoors, outdoors for any extended period of time, you will need an alternative to fill those gaps when GNSS is missing. But assuming that you're without GNSS for an extended period of time, your IMU is behaving or performing to the highest level that you can achieve, the only other option at that point is to use an additional sensor that can help you to reduce the IMU drift in between GNSS updates. So that's what we're going to focus on now. So really on that third point, using a third or a fourth or a fifth sensor is one way that you can get over the fact that the IMU suffers from random walk and scale it back to being the correct solution over time. The problem with that solution is that integration of a third or fourth sensor is never just linear in terms of the complexity of integration. There are different error models to contend with. There's different accuracy capabilities. There's the absolute versus relative argument, and the suitability in different environments will be massively variable, where it's not just open sky or not open sky. There's a whole spectrum of what the environment can be like, including weather conditions that will affect other sensors that aren't GNSS in very different ways. So taking that into account, we'd like to ask a second poll question, and Pete's going to pose that to you with the options now.
Right. Yeah, so just before we get into how OxTS ourselves are looking at this and how we can tackle GNSS denied navigation, we're interested to know whether you already have a solution and what does that solution look like? Or maybe it's not currently good enough, and that might be why you're on the call with us today. So yeah, please do let us know what you're working with right now. And again, it will help us kind of colour the conversation later on, but also for future webinars and our development as well, so that it can relate more appropriately to your needs and use cases.
And you can pick multiple options, can't you, Pete? I think so.
Yes, yeah. So please select
in
all that apply. Yeah, exactly. And so it might be that actually you're using multiple of these and they're still not good enough. That our collection of this data afterwards will let us see those link ups. So if you're just using an INS and it's still not good enough, we can separate that. Okay, I'll close that there. Thank you very much. We've got a lot of people obviously using an INS, and then a few people with wheel speed, and almost the majority currently saying that their solution is not good enough for GNSS and navigation. So hopefully we can talk you through how OxTS are taking on this challenge now. And I'll hand back over to Paris to take you through that.
Okay, so on the topic of using additional sensors, then we're assuming that OxTS's effort to use GNSS and IMU to the maximum of its potential it has exhausted most of what we can eke out of it. The options that we can see in front of us today for additional sensors are divided into two categories. One is install your own infrastructure and create effectively what is a replacement for GNSS in a localized sense. So one option is ultra wideband, an alternative positioning system that can give you an XYZ location based on a number of beacons and anchors mounted in an environment, and then your vehicle moves around within the environment, or your payload moves around within the environment, and with line of sight to those anchors, it is able to give you an XYZ location in a space. So OxTS have integrated with a company called POSIX to offer this solution, and that is a very good method if you are working in the same environment day in, day out, and that is your test and validation area. Often it will be a facility that you own or maybe rent out, and it is installed by a third party at a specific test site or something like that. But that obviously comes with its own downsides. Being infrastructure based, it is inherently in need of being installed and calibrated and maintained, and the anchors will need to be powered and linked via an Ethernet connection. And that comes with overheads, so someone would need to be responsible for that installation. It would restrict you from working in a public space unless you had an agreement with the owner of the public space. So it has pros and cons, but we do have that solution available to anyone working in a private facility where they want to install this. So by all means, if that option works for you, for your application, then do get in touch with us and we'll take you through what is needed, and we can quote for that today. And then the other option is inside out tracking. So something like a LiDAR sensor that has no idea about the world or where it is in the world, but it knows what it can see from its location. So it will effectively give you ranging data to any point in 3D space, as long as the LiDAR laser return hits the thing and comes back into the sensor's measurement. This comes with its own pros and cons, which we'll discuss at length, but it is good in the sense that it is a mutually exclusive sensing method to something like ultra wideband, which shares a lot of commonalities with a system like GNSS in terms of being infrastructure based, line of sight requirement, and effectively you need to connect to someone else's service in order to use it. So focusing then on using LiDAR as an aiding input, we know that LiDAR can give us a distance to a point as a scalar value. It can give us the angle of that point in terms of azimuth and elevation. And it also is a very, very high data rate in terms of how many points per second you get. So it's a good high update rate system, whereas GNSS is a low update rate system, and it's very good in terms of local detection in terms of up to 100, 200 meters, as opposed to having to track satellites that are hundreds, thousands of kilometers out from the sensor itself. So what you can then use this raw data for really falls into three categories for the applications that we are involved in. The first one for autonomous vehicles is instantaneous decision making to avoid an obstruction. So effectively tracking a pedestrian in front of you, taking the necessary steps to avoid that obstruction or purely bring the vehicle to a stop safely is one of the applications, but that doesn't really require an INS at the heart of it in order to monitor that ranging data to an object and then make sure that that range value never hits zero, effectively indicating a collision with the object. The second option is creating georeference point clouds. So taking the INS's location at any given time, synchronizing that INS data to a LiDAR scan, and then georeferencing it about latitude, longitude, altitude, and rotating it around a heading, pitch, and roll value to give you a point cloud in effectively a global frame or a local frame that is has its origin set at a known global coordinate. And then the last option is to effectively take what are georeference points in a point cloud, identify that those are fixed points in the environment, and reverse engineer your own location based on reversing the calculation done through the distance and the angle of the LiDAR return to infer where you are in 3D space or where the INS's measurement point is. And that's what we will talk about in more depth now. The result of georeferencing those points assumes that you know where you are to an accurate location at a given time, and that is done through the ability to use GNSS and IMU data to get that accurate latitude, longitude, altitude, and heading, pitch, and roll. And then you know, say the wall or the street lamp, you know where to place that in your 3D space in your point cloud. If your own position is unknown to a high level of accuracy, you would get very unclear point clouds being georeferenced, and you really wouldn't be able to use the data for much. To take it then a step further, this point cloud on the right hand side here, red points are arbitrarily georeferenced points that really don't mean anything other than an XYZ point has been placed into the point cloud. Blue points are edges or planes that have been detected that can be used for navigation. So that is effectively an anchor, where an ultra wideband anchor or a satellite in the sky technically can count as an anchor to triangulate your own position. All of those blue points can be used to effectively anchor where you are in 3D space. And then the yellow dots are position updates from the system where it has inferred its own location based on the location of all of those points. So at a very, very high level, the idea is that if you can open your eyes after a period of having no idea where you are and you can see the Eiffel Tower, you would by and large be able to know where you are on the global frame. There is obviously a chance as well that you could be looking at the Eiffel Tower in Las Vegas, and so identifying one landmark cannot be enough to know exactly where you are to a precision level. And really that applies to GNSS, it applies to using LiDAR as well. If you can identify a number of anchors in your 3D space, then you can infer your own position and you can reduce the error that that position has in terms of your own location by identifying more anchors in a wider spread, both in the horizontal and the vertical frame, so that you can reduce your error margin, just as you can with GNSS. If you had all of your GNSS satellites overhead, you would have very poor range accuracy in the horizontal frame, because that red region where the error margins of the satellite range overlaps would be spread out kind of in a flat but very wide profile. As you get more anchors around you, you reduce the area of that dilution of precision and you get a better solution. And that's the reason why with the GNSS solution, we quote an altitude accuracy that is about 50% worse than a horizontal position, purely because we do not have any satellites underneath us in order to reduce the dilution of precision in that axis. With LiDAR, however, you can have features above and below you and ahead and behind you and left and right of you. So you can achieve a reduction in that error margin in a different way. So it's coming back to that point where the error model of inside out tracking complements the error model of a GNSS or ultra wideband system, wherein they don't share the same error growth or error profiles. And so if one is working badly, it's very possible that the other system will be working very well. And so that's where we're leaning into picking sensors that don't just share the same error profile and adding more of them to the same loop. We want to overlap in a very kind of complementary way where we can cover more bases with the overall solution. So this is some real world data as an example. This was a multi-story car park with an outdoor area where we started at the bottom left with RTK. We entered the car park, this bottom right section, drove up through the levels and up to the top floor and then back down through the levels and back out. The colouring of the points is based on navigation estimated accuracy. So blue is good centimetre accuracy and red is poor, worse than 50 centimetres accuracy. And as you can see, you can make out the car park, but you can also make out what I can admit is not very much not real data in terms of not the real world being recreated in a digital twin. And the reason for that is on the bottom floor or the middle floor of the car park, a bad GNSS velocity update was received by the system. And in its effort to use GNSS when available, that poor GNSS velocity update was used and accepted, and then GNSS dropped out completely. And if your last velocity update was wrong, it will continue to use it until a new update comes in. And because these sides of this car park were open, that meant that it got a glimpse of a low-level satellite spread, enough to get an update and infer a velocity update, but it was obviously not the right thing to do. So with the default settings of the INS being used as you would use it on the proving ground, this was the result. You can see though, when we get to the top floor, the data becomes good again. We relocked onto RTK and the lampposts and the fences on the top floor were georeferenced accurately and have a good estimate of accuracy again as well. And then when we come back down, some of the data was good for a short period, but then is estimated to be quite poor again. So the result when adding LiDAR aiding is exactly the same raw data input, but using the LiDAR data that we used to georeference the point cloud before has been used. It has inferred a velocity update in 3D, and it is effectively the IMU and the LiDAR velocity has conflicted with that poor GNSS velocity update, and it has then intelligently rejected the poor GNSS velocity update, which has stopped the position being dragged away until we've come back up to the top floor, and we get much better results in the sense that you can absolutely make out that that is the multi-story car park as it looks in real life. You can make out the fences and the cross structures on the middle floors in much more clarity versus the before data. And that really is the concept in a nutshell, where more data being more accurate more of the time, which also helps to relock your position onto RTK when you emerge, because your drift has been reduced in a GNSS outage. So here is another, just a bird's eye view plot of that exact data that was used to georeference this point cloud. So you can see the red plot when we were in the car park and a bad update was received and the system started to drift. It then didn't come back again until we had exited the car park, and then the system snapped back to its actual location. But in that time frame, the Kalman filter does build up error propagation, and sometimes it takes a few corners for it to actually validate itself again before really locking on to RTK again. Because all of the accuracies it estimates are relative to its predicted update, it can receive RTK again and believe that the RTK update is unexpected because it's so far off the trajectory of the INS at the time. And so it's very important that that RTK update is received consecutively for a number of updates before it starts to believe it again, so that it can model its new trajectory properly. So the blue line you can see, hopefully, is a much more accurate depiction of driving into the car park. We drove all the way up to the top floor in a corkscrew, turned around, reversed on the top floor and drove back down and drove back out to the same spot again. So there are two blue plots there where on the in direction, the red and the blue plot overlap really well. And on the out, you can see that the red line deviates from the blue line in a significant way. So that's why LiDAR rading has potential, and is why we're using it in prototypes today to try and reduce that drift, as well as allow people to operate in not just fully GNSS denied environments, but areas where GNSS is poor. And if GNSS is the only thing limiting your IMU drift, it can struggle at times to maintain a trajectory when conditions are particularly interfered. So we've just got a third poll question now.
Thanks, Paris. And those things that you've seen on your screen now, that's been done through post-processing analysis for us to visualize that for you. And so we're interested to know, what does your application need as well? Is it a real-time or is it post-process data analysis? Quite often, especially in the automotive world, we're working in real-time data analysis. We're logging somewhere else, and that data is being used immediately to understand what's happening, or whether the test, for example, can continue. There's been moved to a post-processed world. That's where we see survey users quite often, and so we're interested to see the spread in comparison to the applications that we have in mind today as well. There's a lot of processing power required as we start to introduce these additional sensors, and there are then steps that you can take to make that more accessible, that data more accessible to you. And one of those is focusing on the post-process data analysis first. But as I say, interested to see where people sit across the applications that you've also said that you're interested in. And we've had the majority vote already, so that's brilliant. Thank you very much. We've got a real mix here, and the majority are post-process or users of post-process, and only a few very specifically only real-time. So that's really interesting to know. Thank you very much. I'll pass back over to Paris now, and I'll return in a few slides' time.
Okay, so to try and put it into perspective, anyone who is used to reviewing OxTS data to date would know that NCOM data that we output, which is our proprietary navigation data format, it gives you a position accuracy that you can plot in NavGraph or you can plot in NavDisplay, and that will differ based on the environment that you are operating in. So this graph, hopefully I can go some way to articulating. The sections where the data, the graph plot is green, is sections where GNSS conditions are good. Yellow sections are where GNSS is interfered but not completely missing, and then the red section is equivalent to being in a tunnel or a GNSS tunnel where 0 satellites are in view, and so you're basically drifting at the rate that the IMU random walk affects you. So there are varying levels to the quality of the solution that you can effectively use. So where we were 2 years ago using dual constellation INS in real time would have been this kind of starter for 10, the dark grey line at the top there, where on a proven ground with dual constellation GNSS, we were able to achieve RTK no problem, and customers are absolutely able to execute their applications without any issues. As soon as you start to go into the open road environment or tree covered or high-rise buildings, then naturally GNSS availability drops and you start to get more RTK dropouts. So the idea that if you add more satellites to the mix means you get less time with your data in a harsh environment where you aren't getting good GNSS updates, because you have a bigger pool of satellites, you can achieve 6 satellites line of sight connection more of the time. But even then, depending on the GNSS environment, it may be so bad that you are still getting drift in times where you may have 6 satellites, but the signal quality is not good enough, or you're also receiving from those 6 satellites multipath signals which are conflicting the solution. So GNSS alone in an urban environment, and especially in a tunnel, do not suffice in terms of getting you that centimetre accuracy. Adding a wheel speed sensor, a WSS is what this refers to, will mitigate drift when you have a GNSS outage. So that takes you from your orange line to your light grey line here, which is great. It lowers the error profile over time, but eventually, if you were in a GNSS outage for long enough, you would still get an error profile that grows exponentially, and your system would inevitably have that drift, which may mean that your data becomes unusable, or it may get close to your threshold of when you can or cannot use it. But you also have the option to use a number of other techniques. For example, using combined post-processing. So if your application is not essentially real-time and you can export the data in post-process, you can take advantage of OxTS's combined processing. So that the best example is if you enter a tunnel and it's a 60-second tunnel, instead of the biggest amount of drift occurring at the end of the tunnel, just before you emerge into open sky, your midpoint of the tunnel would be your point of maximum error, and that is depicted by the three lines here, the yellow, blue and green line, where we are assuming you are using post-processing combined solution to get the best data. If you then go back to what we've talked about most today, which is using LiDAR rating, you have a number of modules in a LiDAR rating solution that you can use. So the first is odometry. So that is like a 3D wheel speed sensor, giving you 3D velocity updates that helps to mitigate your IMU drift when GNSS is either poor or completely missing. And that can basically do exactly the job of a wheel speed sensor, but in all axes. So you can mitigate your 3D position drift in a very big way and really shallow out your error curve. If you then also can, in your application, afford to come back through the same location, either the opposite direction or the same direction a second time, then you can take advantage of a concept called loop closure, which will identify the anchors in a location that you have seen before, and it will limit your position drift to effectively re-triangulating your position based on where those anchors were geo-referenced the first time. If you then also get RTK updates, for example, in the section in the graph here where you get the green sections because you've received a good RTK update, that can act as a loop closure event as well. So your error propagation in these periods resets back to 1 centimetre accuracy, and then your error profile starts to build again between those points. So Quad Constellation helps us get more of those green sections, and then wheel speed sensors, combined processing, LiDAR rating help us to reduce the drift in between those sections, hopefully to the point where you get down to centimetre accuracy again, and you can do more data collection in a GNSS denied environment. And the benefit of something like loop closure in a multi-story car park is once it is geo-referenced your anchors in that place with good accuracy, you can then operate for a much longer period of time indoors with no drift, because it will identify those anchors, mitigating your drift to a large amount every time it sees them and reducing that error profile back down to the centimetre level. So that combination of technology working together and is a real mixing of real-time world and post-processing world, and kind of relying on GNSS and not relying on it, is the way that we are tackling the problem and hopefully giving you more data that you can use. So that leads us on to poll question 4.
And quite a natural one following on. Essentially, what level of accuracy do you require for your applications? As we've kind of just talked about of how we can improve our position generally, we'd like to know, related to your application now, what kind of accuracy do you require? And knowing this, again, it will enable us generally in our conversations moving forward with this, is at what point we can really come to and go, hey, we can really solve your problem and provide you with the data and the accuracy that you require. And so we've got sub 30 centimeters, and that one has been chosen generally as an understood lane level position for vehicles on the open road. Sub 5 centimeters as a kind of acceptable level of accuracy on the open road for some validation testing, and then sub 2 centimeters quite often sort of quoted within the accuracy requirements of surveyors. And we've had the majority vote again, so a majority vote there is sub 5 centimeters, with a few also wanting sub 2 centimeters. So thank you very much for that. That's really useful. And as I say, it will allow us to come back to you and say we can solve your issue. We can give you what you want on the open road or whichever application you're working in. That's that one done. Thank you.
Okay. So really then, the result of all that working in tandem should lead to more usable data in more environments, which means that you can do more of your tests on the open road in more real-world scenarios, where you can trust the INS data as that reference data set so that you can validate onboard sensors quicker, more accurately, and more reliably. And hopefully what that means for you as users of ground truthing products is that you can go to market not just with better features, but also go to market quicker, because you can isolate issues and you can resolve them, or do more investigations or do more development to make them better. So that's our goal. And then that really brings us on to the last poll question before we can open it up to questions.
Yeah, brilliant. And so yeah, as Paris just said, if you do have any questions, do start throwing them into the question interface of part of the GoToWebinar side panel that you have, and we can pick those up at the end. But for now, just this last one is really for us in being able to come back to you and chat with you about your needs. Is when are you preparing to take on these tests? Maybe you already are, and you're looking for the solution that can really solve that issue right now, or maybe it's very near future for you, and long-term future vision of what you want to be able to do as well. So this will just help us in being able to understand who we need to talk to, when, and also the kind of appetite for this solution in the market as we see it as well. And quite a lot of you, as I think we would have hoped as well, is quite a lot of you now are looking to take on these tests and get the data that you need. So thank you very much. I'll close that one now. And now really it's time for you to ask questions of us. So I'll close this one down, and now it's over to you. And so we have a first question, Paris, from Jeff, which is what LiDARs in particular at the moment are OxTS working with for this solution?
If you go onto our website, you can see a number of supported LiDAR in our georeferencer application, and we have been working directly for the LiDAR aiding stuff with Velodyne and Hesai LiDAR because the quality of them has been good, and it's helped us to kind of isolate data quality where we want it in the short term. In theory, we can extend that functionality to other LiDAR models and manufacturers. It's just a case of integrating the decoder and getting it to the point where it looks the same to the navigation aiding, as long as it is a rotational 360-degree LiDAR like the VLP16 or the XT32 from Velodyne and Hesai respectively. But the concept is, if it's a LiDAR that can get a full view of its environment around it, and it rotates so that it is refreshing its view of the environment between scan rotations, then we would be able to use it to reduce 3D position drift over time.
Brilliant, thank you, Paris. And just leaving a bit of time for any others to come in, we've obviously got contact information here for both of us, but also just more generally. So if you're interested in what we've been talking about today in terms of wanting to have access to it, to understand what our development plan looks like for the future and being able to deliver this, then please do get in touch. We'd love to have a conversation with you, understand how we can support you and where to take it next. We do have a couple of others. One of them is it possible to upgrade our OxTS RT3000V3 with a LiDAR for this purpose? Or do we need to buy a completely new system?
It's not tied to hardware functionality, so it would any existing user of an OxTS system will know about our feature code licensing. So in time there would be a firmware upgrade as well as a post-processing engine upgrade to check a feature code on your system, and you would be able to then post-process the data regardless of the unit. So we would say it needs to be a V3 INS because of the architecture within the system. It now runs firmware. If we are not updating firmware from V2 and earlier, so it would have to be V3 or later, but certainly an RT3000 V3 would be compatible to be upgraded, yes.
Thank you. And then one that I'm happy to take on as well, which is, in a car park, do the POSIX points just need to be mapped once? And is this done during install? So yes, with a POSIX installation with ultra wideband, there's the general installation of the infrastructure that you have, and then there is a you survey those in so that you can get the best possible known accuracy of those anchors to help with our positioning updates, and that's it. So unless you move them or you add in more, you only need to map once. If you're adding in more, you only really need to update those ones that you move or add to your system. So yeah, it's generally a one and done installation with POSIX to provide that infrastructure base aiding for you. And then I think there's some questions that I think we'll pick up offline as well. And we've just had a new one in, Paris, which is, what about the accuracy of the vehicle angle? Is that enough for you to answer?
Well, there are three angles, I guess, that I could address. So the heading, pitch and roll that we are outputting. Pitch and roll are the easiest ones to address, in that gravity is never not there. So we can always use gravity to infer pitch and roll accuracy. And in evaluations, we have seen very, very little pitch and roll drift in a GNSS outage. The massive overriding contributors to drift are position and heading, because heading is calculated as a result of a velocity vector from GNSS or dual antenna from GNSS. So both of those heading solutions rely heavily on GNSS being present. So the good thing about LiDAR is that, especially if you've got the LiDAR rotating in the horizontal frame, so you've got it mounted flat on the roof, you have your rotational axis of your LiDAR perfectly in the frame of the heading axis of the vehicle. And so in order to match scans between LiDAR scans, you obviously then need to be able to infer what your heading change was of the LiDAR, which means you can infer a heading change of the vehicle. And really that will be a factor of LiDAR angular accuracy in terms of the motor accuracy and resolution. So to take one example of the Velodyne VLP16, which has at 1200 RPM an angular resolution of 0.4 degrees, or at 300 RPM has an angular resolution of 0.1 degrees. So it's reasonable to assume you could achieve updates of that level. And then obviously, if you ever get a GNSS update again in that period, or if you have good detection of anchors near and far in your LiDAR range, you would be able to get that almost like the position dilution of precision reduction. You would be able to reduce that accuracy further, but you would be in the order of 0.1 degrees with the LiDAR we're using today.
Brilliant, thank you, Paris. So there's a couple that we'll pick up offline, I think. But other than that, I think they're the questions that we've had so far. No more further in, and we have now made it to the 45 minutes time, so I don't want to hold people if they're ready to jump off. So really, it's for us to say thank you very much for joining us today. We hope that you've found this interesting, and also that you might be interested in chatting with us further about this solution and what it can do for you. As we say, if you want to contact us, please do. You have both of mine and Paris's emails on the slide for you right now, or you can just get in touch with us more generally at info@oxts.com, especially if you're interested in the ultra wideband solution. It's probably best to go through info@oxts.com and they will be able to support you. But other than that, Paris, do you have any final words?
No, just thank you for attending, and like we said at the start, please do get in touch if you have any requirements for POSIX integration or this LiDAR rating because of your open road, public road use cases.
Well, thank you very much, everybody. I hope you enjoyed the rest of your day, and hopefully we'll see you on one of these webinars again soon. And do look out for the wrap up where you should be able to revisit the recording if you missed anything. So thanks again, and speak to you soon.
Thank you, everyone.